Welcome back to ECE 501B. This is one day removed from our last time of seeing each other, so we have to get through the entire second book in 2 lectures. That's the plan. We probably won't make it. We may only get through the first couple of chapters, but I want to establish the connection between what we've been doing with finite dimensional vector spaces with infinite dimensional or functional analysis. I sometimes don't like to tell you this up front, but I don't think any of this will be on the final exam, the next 2 lectures. But I want you to have information that will allow you to connect. Yeah, everybody disappeared. If you hear the doors banging, that's the reason. I somehow just announced that you were finished for the semester. But you aren't quite finished. You still have homework number 8 and the project deliverables number 2 and number 3. You can include those as 1 file or 2 files in your Dropbox, I think. You should be able to. And teacher course evaluations, those are anonymous. I have no idea who is saying what. They're online, and I do appreciate you filling those out. And the more that I see in terms of the fraction of people, the more believable I am, the more reliable that is as far as representing the entire class's perspective. And a lot of times, if I say, well, here's what the TCEs are telling me, somebody might say, yes, but you didn't have a high enough fraction respond. So I need to get as many responses as possible to get that percentage up, and then it's a little bit more believable as a data set. And I guess after this course, you probably know a little bit about that, or maybe even 503, combining that with this. You know about percentages and probabilities, etc. But today what I want to talk about is the second book, which is Signal Theory by Franks, Functional Analysis. And actually what I want to do is, you've probably heard the analogy of if you're a carpenter, or if you're very skilled with a hammer, you approach everything as if it can be solved with a hammer. Now you have this finite dimensional framework, and our hammer, so to speak, is going to be eigenvalues and eigenvectors. And we'll now translate that, or try to use that, to connect with this new infinite dimensional functional analysis material, and we'll try to motivate that by looking at convolution as a linear operator. And we'll see that if we start expressing our eigenfunctions, not eigenvectors, but eigenfunctions as these complex exponentials, we now have a Fourier expansion environment, and we can start looking at the Fourier transform as if it were eigenvalues, equivalent or analogous to the eigenvalue concept that we've been dealing with in finite dimensional vector spaces. And we'll look at then how do we start to quantify these infinite dimensional objects in a way that might make it more manageable. And in that sense, we might want to establish sets of signals. We looked at sets of vectors, and then we started saying, when do these form subsets? When are these linearly independent? What are the distances between these vectors? We want to start thinking about those kinds of ideas and concepts when we now have not vectors as columns of numbers, or these tall, narrow vectors, but now we have vectors that are functions or signals. And can we now start to relate the ideas of a norm of a signal, the distance between 2 signals if they're in the same signal set? Can we talk about inner products, and what does that mean, or how does that relate to the concepts that we've been comfortable with talking about before? And we might want to think about slicing and dicing different sets of signals, or collecting those and forming certain sets that are equivalent to each other. And we can create some very easy or some very basic ways of partitioning sets into 2, 3, some finite number of subsets that we can then look at and call the different sets within that partition equivalent, or the signals in those. As a very high level, at a very high level view of the book by Franks, which is signal theory, you can think of the first 5 chapters as the foundational piece, and the next 5 chapters as the application of this piece. And now, just to sort of get us thinking, if we're talking about signals, what do you think of, or what comes to mind when somebody says, "Oh, I have a signal"? What does that bring to mind if somebody says, "I have a signal"? They want to say something. And what does that something, if they say something, carry? Or what does it contain? It contains information, doesn't it? So this signal usually carries information. And that's the generic understanding of what a signal is. Does it carry information, ones and zeros, highs and lows, or some other information? And we might want to know how are signals classified. For example, is this, if it's an energy signal, does it have bounded energy? Does it have infinite energy? Is the signal limited in bandwidth? Is it band limited? After a certain frequency, do we no longer see any content? And how might we represent? So how are signals classified? And represented. And the way that we will do that is through what Franks calls this signal space viewpoint, or in his, which is in the book Signal Theory. So our signal space, we've been thinking about vector spaces. Now we have vectors that are signals. We're going to now be in this signal space. Viewpoint provides a geometric way of looking at, or view of, signals, and the way that we can process those signals. And signal processing operations. And again, what we're trying to do is connect what we've spent the semester trying to understand as far as finite dimensional. We looked at vectors, sets of vectors, then we said, are these vectors linearly independent? What do they span, or where can they get us in a particular space? Is there a null space? Those kinds of ideas. Then we started decomposing these vectors into a basis, and once we had that, we started looking at operators and saying, how does this operator map us into a different vector space, etc. And we want to now start to compare or connect the previous material that dealt with finite dimensional spaces. We want to now extend that to infinite dimensional spaces. As far as a general introduction and motivation, let's just start with something that we're comfortable with or that we've been playing with. Suppose that we now have a list of numbers. Where that list, let's say x, is now x1, x2, up to x sub n. And suppose now that we want to visualize that list of numbers, so let's now plot the values. Where we might start with a list that's 8 coordinates long, or has 8 components. Where I is our index. Here is x sub I that's plotted. We now are looking at little n equal to 8, and maybe we have the following. Maybe at index 1, x sub 1 is now 1, for example. Maybe x sub 2 is 2. Maybe x sub 3 is between those. Maybe it's 1.5. X sub 4 maybe now is a half. X sub 5 is maybe minus 2, etc. But now we have a way of visualizing these 8 coordinates in some list of numbers that we're calling x. Suppose now that we look at a larger list, but maybe it's still over the same distance or length of what we might consider time. Now we have I, and we're going between 1 and 16. But now maybe we sort of cut all of that in pieces or in finer resolution, so that now we have and I'm not connecting all of the dots, but you can sort of see that we're starting to maybe have a finer representation of these dots relative to going from 8 coordinates in our vector x to 16. And you can see that if we keep resolving this list into finer and finer subdivisions, as n, the length of that vector, goes off to infinity, now x starts to look a little differently. Now it starts to look like a function. Where now maybe we have x and this is now, as n marches off to infinity or approaches infinity, I now becomes this continuous variable, and x sub I now just flows into a function that might be represented by that solid line or that continuous line. And in this case now, we have an infinite dimensional vector space. And we may call it something a little bit different than to distinguish between a finite dimensional vector space and an infinite dimensional vector space. Now this infinite dimensional vector space may be called a signal space or a function space. but we had a lot of power when we were dealing with certain kinds of operations on our finite dimensional vector space, and one of those powerful concepts was the notion of it being linear, and we can now carry that over into this infinite dimensional signal space or function space, and we can say that it's linear with the standard definitions of addition and scalar multiplication. And with that underlying sort of motivation, we can actually see that many of the results that we've done for finite dimensional cases we can actually apply directly to this signal space or function space domain. Let's look at a motivational example. And what we want to connect with is the fact that we're very comfortable, I hope, at this point in the semester with linear operators and the idea of eigenvectors, and the way that we can actually decompose a vector in terms of these eigenvectors, or the vector representations in terms of eigenvectors. Now, if you're studying for the final, hopefully this comes as no difficult challenge. What's the eigenvector-eigenvalue equation that you're hopefully very familiar with at this point? We now know that this linear operator t applied to some vector v sub I, if that vector v sub I is an eigenvector, now can be described as a scalar weighted version of that eigenvector. We haven't changed the direction. We basically start with the vector v sub I. It gets processed through this operator, and we return to v sub I. It's just now maybe scaled by this scalar lambda sub I. What happens if we now take this same concept, but we look at it instead of eigenvectors as eigenfunctions? Or now let's consider what this would look like for eigenfunction. We can still use the same notation for our linear operator t. Now let's set that off with a function, or have it operate on a function, u sub I of t. This, let's call this the I eigenfunction. And if this is supposed to be similar to our eigenvalue-eigenvector equation, then this must be, when we apply this linear operator to this eigenfunction, it must produce a scaled version of the eigenfunction. Or now lambda sub I is now weighting u sub I, where this lambda sub I we can now view as the ith eigenvalue. And what we want to do now is look at this expression in terms of something that maybe you're already familiar with. I hope you're already familiar with the following. Let's consider this linear operator that we're labeling as t. Consider an operator you're already familiar with. And we will restrict our attention to linear time invariant systems, and the operator that we're interested in, as foreshadowed in the beginning of class, is now convolution. If you remember the convolution integral, now I do have everybody heading to the door. What was that? Suppose now this is our output y of t, and we now want to say that that's the result of convolving a signal x with a signal h. So that now, let's say that our variable of integration is tau. We integrate from minus infinity to infinity over tau, and we now take x of t minus tau. So now we can sort of view this x as being flipped and slid, with t being the sliding variable inside the integral. We weight that or multiply that by h of tau, and then, as I said, our variable of integration is tau. So we integrate with respect to tau. This is now a convolution integral. H of tau, depending on what you're viewing this as, h of tau might be describing a channel. It might be the impulse response of a system, and x is the input to that system, and now that's generating some output y. But we might now be able to just collapse all of that down and say, oh, we have a linear operator t applied to an input waveform x, where this linear operator t is taking our input vector, which is x, it's taking x of t, and mapping it to our output vector y. Our x is now a function and y is a function, and we want to know, how does this linear operator influence the input to produce the output y? Or we could, if you're coming from an engineering background, you might be very comfortable with thinking of this in terms of a block diagram description, where now you have the input x of t being applied to a system modeled by its impulse response, for example, producing the output y of t. In either of these cases, where we have it described by the convolution integral, which we're now collapsing into this linear operator t, or in this block diagram description, t is an operator. How did we use operator before? How did we define an operator? So now the input vector space is mapped back into, or the output vector space is the input vector space, meaning our operator, our linear map, which now is an operator, maps from one vector space back into itself. That's how we've used the operator, and that's true here. T is an operator because both the input weight function x of t and the output function y of t are in the same space. Meaning maybe x is a voltage and y is a voltage waveform. And now h of t might be a filter. You now have this relationship, this operator that maps x into y, whatever h is going to do. What we want to do now is see if we can identify these eigenvalues and eigenfunctions associated with this convolution operator, or this linear operator that we're now designating as this convolution. Let's make a claim. Let's go ahead and claim that e to the I omega t is an eigenfunction of the linear operator t. Our convolution integral, which we're representing by this linear operator t, now we're saying that t applied to these complex exponentials, and what is e to the I omega t? Is that too vague of a question? What do you see when you see e to the I omega t? This now you could just think of something rotating if you wanted to. Maybe it's spinning. And now what's the magnitude of e to the I omega t? It now has a magnitude of 1, and the rate that with which it spins is omega. But now we have, and t is telling us sort of, if you pick a t and an omega, you can find where that dot is in this spinning process, or where the tip of that arrow is, or the head of that spinning vector is. We now have e to the I omega t, but omega is a continuous variable, meaning we have all frequencies available, and t is also a continuous variable from from 0 to whenever we want. So that now we want to know, how does this convolution integral map e to the I omega t? So let's check that out. Let's see what happens. Let's say we want to check this, and we're going to check it by saying, suppose we let our input waveform x of t be e to the I omega t. And now e to the I omega t is just a collection of sinusoids, is one way of thinking of that. I give you a w, you now have a sinusoidal waveform. And you can think of this through Euler's equation. You can view e to the I omega t many different ways, but you now, when you see that, I like to just think of that as sinusoids. E to the I omega t is just a collection of sinusoids. If we've now put, or called x of t, this collection of sinusoids, let's now put that structure back into this convolution integral. This specific structure, e to the I omega t, let's now use that to replace x of t minus tau. Or now, x of t becomes an argument, or has as its argument, two different variables, t and tau. Or y of t is now this integral from tau equal minus infinity to infinity of e to the I omega, but now it's not t, it's t minus tau, h of tau, d tau. What's our variable of integration? Tau. Omega is not a function of tau. T is not a function of tau. So we can factor out a piece of that. We can now remember that e to the I omega quantity t minus tau we can write as two complex exponentials, the product of two. And let's slide one of those outside of the integral involving the tau, the variable tau. Or let's now rewrite this as this integral from tau equal minus infinity to infinity. We need to keep track of what has tau in it, e to the minus I omega tau, h of tau d tau. But now let's just go ahead and make it very clear that that's setting apart from what we still have in a piece of that, which is e to the I omega t. But what did we say we were wanting to do? We were wanting to have this linear operator t have as an eigenfunction e to the I omega t. But now, if we look at what's happening in the bracketed expression in blue, what is this? This you can think of in a lot of different ways, can't you? This looks like maybe an inner product of the impulse response h with this x, where if we now looked at the inner product of h of t and e to the I omega t, we would take h times the conjugate of e to the I omega t, and we could put it in this integral form. So we could think of this as an inner product, and that now says, how does the impulse response line up with, that's what this inner product is doing, how well does it match this complex exponential? And that complex exponential obviously depends on omega. So for different values of omega, how does h of t align with that? This is now you could think of as an inner product. But you can also start looking, and if that's an inner product, what's the result of that integral? What's going to fall out? Or what are we doing? What's the result of performing that integration operation? What's going to come out of the blue brackets? It's going to be a scalar, isn't it? It's going to be a scalar that's a function of this omega. And what is this guy on the right-hand side? Well, that's just what we started with. That's an eigenfunction. So now we have a scalar times the eigenfunction, and that's what happened when we pushed this eigenfunction through the linear operator of convolution. Or if we wanted to write it now a different way, or in a more compact way, we could say, oh, we put e to the I omega t through this convolution operator, which we're now collapsing down to t, and that produced some scalar we'll call lambda sub omega, since it was a scalar function of omega, that weights e to the I omega t. So it looks like this convolution has as its eigenfunctions these sinusoids, e to the I omega t. But what's this lambda? If we simply write that down by itself, suppose we now say, oh, lambda of omega, we define that to be what's in the blue brackets. That's now this integral from tau equal minus infinity to infinity of e to the minus I omega tau, h of tau, d tau. But have you seen that expression anywhere before? Now take off your inner product lens or glasses and say, have I seen this expression anywhere? Does this look like some kind of transform that you've played with? You might have said, oh, this is now the Fourier transform of this time domain quantity h of t. And what's h of omega? That's a scalar. That's a function of omega. And we were viewing that as it was scaling these eigenfunctions. And what did we typically call those scalars? Eigenvalues. So now you can start to think about this Fourier transform, this frequency domain quantity. And if I fix omega, what's h of omega? If I fix omega at one value, it's a scalar. It has what? It's complex in general, isn't it? It has a magnitude and an angle. That's a scalar. So that now you could sketch the Bode plot of that h of omega. And now what is that Bode plot? That's this continuous collection of eigenvalues. It's the frequency content of your system or your model, your channel, that has an impulse response h of tau. So this now is some Fourier transform. That's now the eigenvalue, or we can rewrite this operator, t of e to the I omega t, is now the eigenvalue, but that's an infinite number of continuously variable over w eigenvalues weighting our eigenfunction e to the I omega t. And where did all of this start from? We started with a continuous quantity for x. So we remember we were moving when we were moving to continuous from the finite dimensional list of numbers. Remember, moving to continuous caused the indices to become continuous as well. Instead of having a finite number of eigenvalues, now we have this continuous expression of eigenvalues, which we're calling h, and we can collect those into their magnitudes and angles, and that's the Bode plot, or the Fourier transform of this system. So that we now have these eigenfunctions, e to the I omega t, eigenfunctions indexed by a continuous parameter omega, which if we now redraw our block diagram, here is our linear time invariant system that now processes these sinusoids, which we're now sort of parameterizing in the frequency domain as e to the I omega t. This is now u of t in the time domain as parameterized over frequencies omega. But we can now think of the output as being this scalar weighting of these eigenfunctions. Or we now have lambda of omega, u of omega of t. And how many eigenfunctions, how many of these e to the I omega t's do we have? Now we have an infinite number of those parameterized by omega. It's this continuous value of omega. And now we can think, or so, we can interpret what we see as h of omega, the transfer function, as the eigenvalue spectrum of that linear operator T. Now that we have this idea, let's see if we can start to use it like we've done when we started introducing eigenvectors. We now said, oh, can you parameterize or decompose any arbitrary vector as a linear combination of these eigenvectors? Now can we do the same thing for these eigenfunctions? You give me a function, x of t, can we now parameterize that in terms of these eigenfunctions? And you know that that's possible, knowing the Fourier theory that you have already in mind. Let's now do that. Now let's recall the importance of eigenvector decomposition when we were analyzing operators on finite dimensional vector spaces. How did we write an arbitrary vector v? In, let's say, a finite number of eigenvectors, e sub I. We just had a1 e1 plus a2 e2, where now we have this arbitrary vector v written in terms of an eigenvector basis. Now that we have our arbitrary vector v written in terms of this linear combination of eigenvector basis, what happens if we put that through or applied a linear operator to that? Now we have t operating on this sum a sub I, e sub I. But remember, that operator was linear, so that now we could slide that in to each of these terms in the summation. And a's, those are scalars. They can come out, which now allows us to do what? Now we have t operating on each of these e sub i's. And what's t e sub I? That's a linear operator, and the e's were the eigenvectors. So now we have this scaling in each of the eigenvectors, or in each of those directions, so that this now becomes this summation a sub I, lambda sub I, e sub I. Or we now have a very simple process that results from using or decomposing this arbitrary vector into its component-weighted eigenvectors. Very simple process results from using eigenvectors as a basis. But how did we get these a sub i's in this decomposition of an arbitrary vector v? How did we find the a sub i's? If we now say, oh, we can arbitrarily decompose any vector v that you give us in this vector space as some linear combination of eigenvectors, now we need to find these a sub i's. How do we do that? Or what was maybe one word that you could say relative to finding each of these a's, a1, a2. So in our normal finite dimensional setting, if I now said v is equal to some linear combination of this basis, how did we find the scalar amount that each of these eigenvectors represented in this decomposition of the vector v? We were doing this inner product type behavior or a projection. So the projection now says that a sub I is the inner product of the arbitrary vector v with the respective eigenvector e sub I. That's what we had in the finite dimensional case. What happens in the continuous case? And now we are assuming x of t is made up of a linear combination of eigenfunctions. So that now we want to find a of omega. We can now view that as the inner product of x with an eigenfunction that's parameterized with respect to frequency omega. Or this is now this x of t inner product with e to the I omega t, where this a of omega tells us really the amount or the quantity of the arbitrary input or signal x of t that's aligned with u sub w, which is e to the I omega t. To see where this takes us, let's just remember the inner product. If I now have a generic inner product, let's say that that's now u of t with z of t, how would I define that for these functions in terms of an integral? Typically, we might say it's the function or the vector in the first slot times the conjugate of the vector or the function in the second slot. So that we now have u of t z star of t dt, and we'll integrate out time. So this is now a functional. It takes two vectors or two functions and maps those into a scalar. Now let's do that for this particular inner product that we're trying to create to define A of W. And these are a way of finding the scalars relative to the vector or the function x relative to these sinusoids, e to the I omega t. Doing that, we now can say A of omega is this integral from t equal minus infinity to infinity of x of t, and now we have the complex conjugate of the second slot, which is e to the I omega t. So we conjugate that, and it's now e to the minus I omega t dt. So that now we have A of omega, which gives us what? This scalar amount by which x is aligned with this particular frequency. So if we had a given value for omega, A of omega is going to be a scalar that's continuous with respect to this parameter omega. We have A of omega, and we have x of t, and the fact that x of t can be written in terms of those A of omega. Those are our scaling amounts, A of omega, and they scale these complex exponentials. So that now, if we wanted to rewrite x of t, we could say, oh, that's the integral, which is now what we have to do instead of this finite sum. We've now transitioned from indices to continuous variables. We're now integrating instead of summing. We're integrating over the index w, or the continuous variable w. That's now A of w, and we use those scalars to weight these complex exponentials, e to the I omega t dw. Where now instead of a sum, we have an integral, because now we're dealing with continuous parameters, w, instead of indices. And these A of w's are this complex scalar that's a function of w, which we can associate with frequency. And you can contrast that with the finite dimensional vector v of t, which was this sum from I equal 1 to n. We had a finite number of scalars, a sub I, weighting our eigenvectors, e sub I. This is now our comparison, which is the finite dimensional decomposition of an arbitrary vector v in terms of the eigenvectors that are now spanning our vector space, and we're representing those as E sub I. Here maybe I'm overusing E. In the black equation, E is 2.713, and the other one it's just a variable. Hopefully it's clear from the context what I'm using that E to represent. E sub I in the blue expression is just a vector, representing a vector. What have we done? So now we have x of omega, another way simply of labeling these scalar, complex scalar coefficients, a sub w, which is now this integral from t equal minus infinity to infinity. We found those weightings by taking the inner product of x of t with these complex exponentials. And this really just a of omega, or capital X of omega, just tells us how the time domain waveform x of t is aligned with these sinusoidal waveforms. If you now say, oh, give me a frequency omega of 27.2, now you can say, oh, how does x of t align with that? Well, that's going to be expressed by this capital X of 27.2. And that will just be this complex number, but now you can think of that complex number as having a magnitude and an angle, and you just keep doing that for all of these different values of omega. And what is that capital X of omega? That's what we've been used to thinking in terms of this Fourier representation of the time domain waveform x of t. Now we have these scalars in the frequency domain. It's a frequency domain picture of what the waveform, this generic waveform x of t, looks like. Meaning we now have different ways of expressing this signal, x. We can think of it in terms of the w basis, the frequency domain basis, these exponentials, e to the I omega t, and we can think of it as we typically do, x of t in the time domain basis. So we have the coefficients of x of t in the frequency or w basis, that's what capital X of W is. So if I give you capital X of W, now you know what X of T is. You know how X of T weights every sinusoidal waveform. Or you could now say X of T, we could also think of X of T as the coefficients in the time basis. X of t, coefficients of x, in the t basis. By that, we have this expression x of t, and now you can say, oh, that we can think of as this inner product of x of w with e to the I omega t dw. And again, this is just our a of w. Meaning if somebody gave us the a sub w's, or capital X of omega, we can now create the time domain waveform. We can just collect all of these sinusoids and weight those by these scalars, capital X of omega, and we can sum them up, we can integrate those, and now we have our time domain waveform x of t. And that's now on the time basis. What does this tell us? Well, now we can sort of think about y of t, the output, in two different ways. We can think of it as this convolution of x of t minus tau, h of tau d tau. That's the convolution in time. But we could also think about that in terms of y of t being written in terms of these weighting coefficients of the sinusoids. Or we might now say this integral from omega equal minus infinity to infinity of capital X of omega, h of omega, e to the I omega t, d omega, where we might see this capital X of omega, h of omega, written simply as y of omega, where this is now, or another way of thinking of this is convolution in time corresponds to multiplication in frequency, where y of w is what? That's like these eigenvalues of y of t. Capital Y of w is now this eigenvalue scalar weighting of these complex exponentials. And I'm sure you're thinking with your cap on, that's your y cap. You now say, why is that true, or can we actually show that? So let's go ahead and see where this relationship comes from, based on what we've just derived in terms of decomposing our signals into this eigenfunction decomposition. So let's start with the left-hand side. We had y of t is equal to this integral from integrating from tau equal minus infinity to infinity of x of t minus tau, h of tau, d tau. But if h of tau is a function, we can decompose that into its eigenvalue, eigenfunction decomposition. Meaning, let's now rewrite that, h of tau, in this expression in terms of its eigenvalue, eigenfunction decomposition. So that we now can rewrite that as this integral from omega equal minus infinity to infinity of h of omega. Those are the eigenvalues, the eigenfunctions that get weighted by the eigenvalues are e to the I omega t. So this is, think again about this arbitrary vector v of t. Now we're replacing that v of t with h. And we say, how do we expand h? H is just going to be this eigenvalue, eigenfunction decomposition, little h of t. So that we've now rewritten this finite sum as integrals, since these eigenvalues are a continuous function of omega. So far, so good, except I haven't carried down my d tau. So far, all we've done is rewrite h of t in terms of its eigenvalue eigenfunction decomposition. Let's now start moving some of these pieces around. Let's put everything under the same two integral operators. So maybe I'm getting a little bit fast and loose with my sliding, but let's just say we slide that inner integral to the outer integral, and now we have tau equal minus infinity to infinity, x of t minus tau, h of w, e to the I omega tau, d tau, dw. This looks a little bit messy, so let's clean it up. Let's do some change of variables. Suppose we now let sigma be t minus tau, where t is a fixed value. That's really our y of t on the left. And we want to do this, we want to evaluate that integral for each fixed t. So if t is fixed, what happens when we take the differential of sigma? T is fixed, so we don't have to worry about that. That goes away, and we have minus d tau. And if we solve sigma equal t minus tau for tau, so that tau is now equal to t minus sigma, let's now use that in this integral expression for y of t. We now have y of t is equal to the integral from omega equal minus infinity to infinity. If we've now converted out of tau into sigma, what are the integral limits on the second integral? If sigma is equal to minus tau, and we started at minus infinity, now we have sigma is equal to, it's now equal to infinity, and the upper limit now is minus infinity by our sigma equal t minus tau relationship. We now have x of sigma, h of omega we haven't worried about, but now we replace tau with t minus sigma in that exponential. We now have e to the I omega t minus sigma. D tau is actually minus d sigma dw. And let's now start collecting some of these terms that have similar variables. Or we now say this is now equal to omega going from minus infinity to infinity, but now we have this integral from sigma equal minus infinity to infinity. And where did that come from? Well, I'm now going to absorb that minus sign from the minus d sigma, and that changes my limits of integration. So now I'm integrating from minus infinity to infinity of x of sigma e to the minus I omega sigma d sigma, and I now have h of omega e to the I omega t d omega. Did I keep track of everything? My limits changed signs, or the limits on this inner integral, because of the minus d sigma. I pulled that minus sign into the changing limits, and I factored h of omega and e to the I omega t out and kept d omega outside. And now what's this in square brackets? That should look just like capital X of omega. And what is that? That's actually another inner product, isn't it? That's the inner product of x. How does x align with these complex exponentials? And that gives us now these scalars, capital X of omega, which you can think of as the eigenvalues of x of t in the frequency basis. If we now collapse all of that down that I've highlighted as capital X of omega, we now have this integral from omega equal minus infinity to infinity of x of omega, h of omega, e to the I omega t d omega, and that's now equal to y of t. Where this now you can think of as the eigenvalue expression or scalar values that weight these eigenfunctions e to the I omega t that make up little y of t in the time domain. This is now the eigenvalue spectrum of y of t. And that's what we were trying to derive, is this relationship of, and that's sometimes why as students we prefer to go into the frequency domain. We can start playing with these products, which might be easier than worrying about convolution integrals in the time domain. We can now form the product of the eigenvalues of our time domain waveform x, the eigenvalues of the system h, and now we multiply those together to get the eigenfunctions of our time domain waveform y of t. And what we've tried to sort of show is that all of Fourier analysis through the lens of our hammer, our eigenvalue, eigenvector knowledge in this finite dimensional space, all of Fourier analysis, dare I say, trivial, but just a trivial result from expansion in eigenfunctions of a linear time invariant operator, which was convolution. Or a key point that could be made is that x of t and capital X of omega are just two different representations of the same underlying waveform x. X of t and X of omega are just different representations where you can think of one being the eigenvalues in the time domain, the other one being eigenvalues in the frequency domain, expansions in different basis, just different representations of the abstract signal x. So you give me a signal x, you can think of it in the time domain, which is now, you can decompose that in terms of the eigenvalues, capital X of omega, or you can now look at X of omega as coming from the time domain, weighting these, or the inner product of the time domain. It's however you want to think about it. How does your x of t in the time domain align with these sinusoids? Or how do you see these the x of t in terms of this weighting, these eigenfunctions, capital X of omega, in the frequency domain. That's now the connection, maybe, between finite dimensional and infinite dimensional. You had the little v, you could expand in terms of the eigenvectors. Now we have a general function, x of t, that's now is decomposed in terms of these frequency weight eigenvalues that weight these eigenfunctions e to the I omega t. And we'll pick up with now trying to decompose or collect sets of sets for different functions that we can now maybe classify in terms of what are the distance between these functions, how do we create norms, etc., in these infinite dimensional spaces like we've done in finite dimensional spaces. And we'll pick up at that point next time.